Welcome back to Fun Facts Online. Today, we are diving deep into a topic that sounds like it was ripped straight out of a spy novel or a sci-fi blockbuster, but it is actually happening right now in chemistry labs across the world. We are talking about the end of forever. For the last century, human civilization has been obsessed with durability. We engineered materials to last. We made plastics impervious to rot, rust, and time. And we succeeded. We succeeded too well. We created materials that outlive the civilizations that made them, clogging our oceans and landfills for centuries. But now, the pendulum is swinging in the exact opposite direction. We are entering the age of programmable polymers. These are materials designed with a built-in death clock. Imagine a plastic bottle that dissolves the moment it touches seawater. Imagine a military drone that vaporizes into thin air after a mission. Imagine sensors that fertilize the soil they monitor. Today, we are going to explore the science, the applications, and the terrifying potential of self-destructing plastics. Let's get right into the hard science. How do you convince a material to commit suicide? The core innovation here is a shift from passive degradation to active, triggered transience. When we talk about traditional biodegradable plastics, like PLA, we are usually relying on vague environmental conditions. You throw it in a compost heap and hope the heat and microbes eventually chew it up. It is slow and it is unreliable. Programmable polymers are different. They are like time bombs waiting for a specific code. The most fascinating development in this field is something called self-immolative polymers, or SIPs. Think of a standard plastic molecule as a long, tangled chain. In a normal plastic, if you break a link, you just get smaller chunks of plastic, which eventually become those microplastics we are all worried about. SIPs function differently. They are designed to unzip. I want you to visualize a long row of dominoes standing up. This is your polymer chain. It is stable. It creates a solid, usable object. But at the very front of this line of dominoes, scientists attach a specific molecule called an end cap. This end cap is the lock. As long as that cap is there, the plastic is strong. But if a specific trigger removes that end cap, the first domino falls. That energy destabilizes the next link, which destabilizes the next, and so on. A single chemical event causes the entire macroscopic object to depolymerize, to fall apart back into its original monomers in minutes or hours. One of the chemical pathways used to achieve this is called quinone method elimination. It sounds complex, but it essentially allows scientists to tune the stability. You can create a plastic that is rock hard in the dark, but liquefies the moment it is hit with UV light. It is molecular engineering at its finest. But chemistry isn't the only way to do this. Researchers are also looking at structure. At Rutgers University, they are using an approach called the origami trick. Nature folds polymers all the time. Look at DNA or proteins. Synthetic plastics are usually just spaghetti-like chaos. By using conformational pre-organization, scientists are pre-folding synthetic polymers into specific shapes. Think of it like creasing a piece of paper before you try to tear it. The paper is strong if you pull casually, but if you pull in a specific way, it tears perfectly along the crease. These molecular creases create programmable weak points. The material holds its integrity perfectly until the exact moment it is needed to fail. Now, if molecular zippers and origami sound too mechanical, let's talk about the biological approach. This is where things get really wild. This is the concept of living plastics. In 2024, researchers from the Chinese Academy of Sciences unveiled a material that is effectively a Trojan horse. They took Bacillus subtilis, a common soil bacteria, and genetically engineered it to secrete a powerful plastic-eating enzyme called lipase BC. But you can't just mix bacteria into plastic. The heat of manufacturing would kill them. So the scientists stressed the bacteria with heavy metal ions, forcing them into a dormant spore state, These spores are incredibly tough. They survive the high heat and pressure of the extrusion process. They sit inside the solid plastic, asleep, acting like a filler material that actually reinforces the strength of the plastic, much like rebar in concrete. The plastic works just like any other plastic, until the surface is eroded or scratched and placed in soil. Once those spores are exposed to nutrients and water, they wake up, they germinate, and they begin secreting enzymes that eat the plastic from the inside out. In tests, these plastics degraded completely in just 6 or 7 days, leaving absolutely no microplastics behind. It is a self-contained recycling plant inside the material itself. So we have the mechanism, the zippers, and the spores. But how do we tell the material when to die? This brings us to the triggers. The programmability of these materials comes from the input required to start the breakdown. We can categorize these triggers into 3 types: the Cinderella, the Wicked Witch, and the Secret Agent. Let's start with the Cinderella trigger, time and light. This is perfect for single-use packaging. You don't want a candy wrapper to dissolve on the grocery store shelf, but you do want it to vanish if someone throws it in a park. New additives can make chemical bonds sensitive to specific UV wavelengths found only in direct sunlight, not the LED bulbs in your pantry. A wrapper dropped outdoors would become brittle and dissolve into wax within weeks. On the military side, DARPA had a program called VAPR, Vanishing Programmable Resources. They looked at polymers that sublime, turn from solid to gas. At sunrise, imagine a vampire drone. It crashes, night falls, the sun comes up, and the drone simply evaporates to prevent the enemy from capturing the technology. Then we have the Wicked Witch trigger, water. This is massive for medical and environmental tech. We call this transient electronics. Labs are building circuits using magnesium for the conductor, silicon nanomembranes for the semiconductor, and silk protein for the substrate. You can program the silk to dissolve in minutes or years depending on how you crystallize it. When the silk dissolves, the ultra-thin silicon and magnesium components just fall apart and hydrolyze into minerals that the body or the soil can absorb. Finally, the Secret Agent trigger, radio and heat. This is for high-security applications. You can embed resistive heating elements into a polymer. If a command center sends a specific radio frequency, it induces a current, heating the polymer to a critical temperature where it instantly depolymerizes. It is the ultimate Mission Impossible self-destruct button for encrypted hard drives. Now that we understand the how and the when, let's look at the where. What does a world of transient objects look like? The applications are already disrupting major industries. Let's go back to the military. The US military loses thousands of sensors and radios in the field. If captured, that is a security breach. The VAPR program and its successor, Icarus, have demonstrated gliders made of these sublimable polymers. They drop supplies to special forces and then vanish. But think smaller. Imagine scattering thousands of dust mode sensors over a conflict zone to monitor troop movements. Instead of risking soldiers' lives to retrieve them, commanders just wait. After 30 days, the sensors dissolve into dust. The environment is left pristine, and the intel remains secure. In agriculture, this technology solves a massive e-waste problem. Precision agriculture relies on data, soil moisture, nitrogen levels, pH. But sticking millions of plastic sensors into farmland is pollution. Researchers at the University of Glasgow and Chicago are developing sensors made from biodegradable polymers and compostable conductive inks. A farmer could print these on a modified inkjet printer, scatter them, get the data for the growing season, and then plow them into the soil. Because they are made of carbon-based polymers, magnesium and zinc, they degrade into micronutrients. The sensor that tracked the crop actually becomes fertilizer for the next harvest. It is a perfect closed loop. Then there is the holy grail packaging. Companies are racing to replace the trillion-dollar single-use plastic market. A UK startup called Notpla is using seaweed to create transparent films. Their Uho sachets are edible. They partnered with Just Eat to make takeaway boxes lined with seaweed that degrade like a fruit peel. But there is another approach by a company called Polymateria. They don't make new plastic, they hack the old stuff. They have a biotransformation technology, a master batch additive that you mix into standard polypropylene or polyethylene. It creates a time lock. For a granola bar, the plastic stays stable for 6 months. If that plastic is littered and exposed to nature after that time, the additive attacks the crystalline structure, turning the hard plastic into a bioavailable wax that bacteria love to eat. It effectively turns pollution into food. In healthcare, transient implants are changing surgery. Right now, if you break a bone, you might get titanium screws. Often, you need a second surgery to remove them. Programmable polymer screws made from silk or PLGA can hold the bone together for exactly 6 weeks, the time needed for healing, and then dissolve. We are also seeing smart drug delivery. Logic gate polymers can release drugs only when specific conditions are met. Imagine a polymer nanoparticle carrying insulin that dissolves only when the pH of your blood changes due to high glucose. It is an artificial pancreas without any electronics. So, this all sounds incredible. Why isn't every water bottle self-destructing yet? Why are we still dealing with islands of trash in the ocean? We have to talk about the economic and industrial reality. The first hurdle is the Frankenstein supply chain. Our global manufacturing infrastructure is built for materials that melt, flow, and harden, and stay hard. Many programmable polymers, especially the enzyme ones, are sensitive to heat. Standard plastic extrusion happens at 170 to 250 degrees Celsius. That creates a manufacturing hellfire that kills most biological agents. The breakthrough with Bacillus subtilis spores was so significant because they survived that heat. But for the rest of the industry, retooling factories is expensive. That is why Polymateria's drop-in solution is gaining traction. It works with existing machines. Then there is the cost premium. Right now, programmable polymers cost 20 to 50% more than virgin fossil fuel plastics. Creating self-emulative linkers is chemically harder than refining oil. And while consumers say they want eco-friendly products, very few are willing to pay 50 cents extra for a bottle of water. However, analysts predict a tipping point. As governments introduce carbon taxes and plastic packaging taxes, like those in the UK, the cost of the old plastic goes up. If a company has to pay for the 400-year life cycle of a PET bottle, a self-destructing bottle suddenly becomes the cheaper option. There is also the recycling paradox. This is controversial. What happens if you throw a self-destructing bottle into a standard recycling bin? If it degrades during the recycling process, it could ruin the whole batch of recycled plastic by introducing weak points. This is a major concern for the recycling industry. The defense here is called switchable degradation. Newer tech is designed to be stable during the mechanical recycling process, the chopping and melting, but to degrade only under specific industrial composting conditions or enzymatic baths. As we look to the future, toward 2030 and beyond, the definition of plastic is going to change fundamentally. We are moving toward programmable matter. We are looking at materials that self-heal, like skin for a set lifespan, and then die like an organism when their time is up. We are looking at swarm robotics, where thousands of microgliders map a hurricane and then biodegrade into rain. But there is a dark side to consider too. If your car is made of programmable polymers, could a hacker trigger your bumper to disintegrate on the highway? As materials become digitized and programmable, they become susceptible to the same security threats as software. Material cybersecurity is likely going to be a new field of study. In conclusion, for the last century, we measured progress by durability. We fought against entropy. But in a finite world, infinite durability is a bug, not a feature. Programmable polymers represent a profound maturity in materials science. We are finally admitting that death is a necessary part of a life cycle, even for our objects. By programming the end into the beginning, We are creating a future where technology flows through the environment like a stream, useful, present, and then, gracefully, gone. The future of plastic isn't about making it stronger. It's about teaching it how to say goodbye. Thanks for listening to Fun Facts Online. See you in the next episode.